Hi everyone, our topic is real-time monitoring of air skin cleaner suppression efficiency. First of all, air skin cleaner means it is a device or implement used to separate a grain from the dust particle or unwanted things. Here we see about data-driven algorithm for optimized grain cleaning operations through continuous efficiency monitoring and predictive analytics. The challenge: variability in grain cleaning. Material variability, grain composition, moisture content and particle distribution change with each batch, requiring constant adjustment of cleaning parameters. Next, equipment drift. Air skins and aspiration systems experience wear over time, gradually reducing separation efficiency without obvious indicates. Next, operator dependency. Current manual adjustment rely on operator experience and predict sampling, leading to suboptimal settings and inconsistent output quality. These challenges result in significant economic losses through grain damage, product contamination and reduced throughput. Without real-time feedback, operators cannot optimize settings quickly enough to compensate for changing conditions, leading to over-cleaning or under-cleaning situations that compromise both quality and yield. Next, current methods and their limitations. Manual sampling and visual inspections. Operators collect samples at intervals and access cleanliness subjectively. Time consuming process with 15 to 30-minute delays between measurements prevents real-time optimizations. Next, laboratory analysis. Send samples to a lab for detailed composition analysis. Provide accurate data but with 2 to 4 hours turnaround time, making it useless for immediate process control decisions. Next, fixed parameter settings. Many operations use preset setting regardless of material conditions, results in conservative operations that sacrifices throughput or quality to avoid problems. These traditional approaches share a critical flaw. They provide historical snapshot rather than continuous feedback. By the time inefficiency is detected, hundreds or thousands of bacillus may already have been processed optimally, resulting in unnecessary grain losses and reduced revenue. And next, proposed approach: sensor fusion and machine learning. Our algorithm combines multiple sensor streams with predictive analytics to estimate a separation efficiency continually without interpreting prediction. Multi-sensor array. Air velocity sensors, pressure transducers, vibration monitors and optical practical counters provide comprehensive process characterization. Machine learning engine. Regression and classification models learn the relationship between sensor readings and actual separation efficiency from historical data. Real-time dashboard. Visual interface displays current efficiency estimates, trend analytics and recommended parameter adjustment to operators. And next, algorithm design. Data acquisition and pre-processing. Sensor signal acquisition. High frequency sampling of air pressure, flow rate, vibration amplitude, motor current and optical density measurements. Next, noise filtration. Apply a digital filters to remove electrical noise and mechanical vibrations unrelated to separation performance. Next, data synchronization. Align timestamps across all sensor channels to create constant future vectors for each time interval. Next, outlier detection. Identify and flag anomalous readings caused by sensor faults or unusual operation conditions. Future vector construction. Combine cleaned sensor data with calculated derived parameters to create input for prediction models. This pre-processing pipeline ensures that machine learning models receive clean, constant data that accurately represents the physical cleaning process. Signal condition is critical because agricultural environments introduce significant electrical and mechanical noise that can degrade model performance. And next, Future engineering for efficiency predictions. Direct measurement. Air velocity at multiple points in aspiration column. Pressure differential across screen depths. Vibration signatures from unbalanced loads. Motor current draw indicating load changes. Optical transmission through material flow. Next, derived features. Pressure to velocity ratio indicating efficiency. Vibrating frequency spectra in identifying material buildup. Current variance detecting material flow changes. Optical density gradients showing separation zones. Moving averages and trend indicators. These features capture both instantaneous state and temporal patterns of cleaning process. Domain knowledge guide future selections. Agricultural engineers understand which sensor combinations correlate with over cleaning versus under cleaning or versus under cleaning. The future engineer phase transforms raw sensor data into meaningful prediction that machine learning models can interpret effectively. Next, machine learning model selection. From regression to classification. In their classification, there are three models. First, regression models predict continuous efficiency scores using random forest gradient boosting or neural networks trained on historical sample data. Next, second model is classification model. Flag operation condition as optimal over cleaning or under cleaning using decision boundaries derived from regression outputs. Next, 3 ensemble methods combine multiple models to improve robustness and reduce prediction variance across drivers operating conditions. Next, model training process. Historical data pairs sensor readings with laboratory measured efficiency from manual samples. The training data set spans normal operating conditions, equivalent wear stress, and various grain types. Cross-validating ensures model generalize to unseen conditions rather than memorizing specific scenarios. And next, implementation strategy, hardware and software integrations. Edge computing platform, Redis industrial computer installed near cleaner process sensor data locally, reducing latency and network dependency. Wireless sensing network, self configuration mesh network connects sensors to gateway, simplifying installation in existing facilities without extensive ring. Operator interface, touchscreen display shows real-time efficiency trends, alerts and recommended adjustment with intuitive visualizations. Software architecture, real-time operating system manages sensor polling and pre-processing Python-based analytics engine, execute prediction models with 1 to 5 second upgrade frequency data history, activate all measurements for retrospective analytics and model retaining. API endpoints enabled integration with facility management system for automated reporting and remote monitoring. Validation and testing, lab to field trials. In their testing, there are 4 types. First, controlled laboratory testing. Validate sensor accuracy and model predictions using calibrate grain mixers with known contamination levels. Measure prediction error rate and refine feature engineering. Next, pilot installation. Deploy prototype system on single layer skin cleaner for 30 days trial. Compare algorithm predictions against manual samples taken hourly. Adjust model parameters based on field performance. Multi-site evaluation. Install validated system across 5 to 10 facilities processing different grain types. Collect drivers operating data to confirm model robustness and facility edge cases requiring special handling. Next, commercial deployment. Full-scale rollout with continuous monitoring to prediction accuracy. Establish retraining schedule as equipment ages and grain characteristics evolve seasonally. Conclusions. enhanced efficiency, reduced waste. First, efficiency improvement. Real-time optimization typically increases separation efficiency by 10 to 20% compared to fixed parameter operations. Next, annual savings. Average cost savings per cleaner from reduced grain losses and improved throughput at typical facility volumes. Next, waste reduction. Decreases in rejected material through optimized setting that avoid over cleaning while maintaining quality standards. This monitoring algorithm transforms air screen cleaners from fixed parameter equipment into intelligent systems that adapt automatically to changing conditions. By providing continuous feedback rather than periodic snapshots, operators can maintain optimal settings consistently, maximizing both quality and throughput. The implementation approach balances technical sophistications with practical constraints of engineering environments, using ruggedized components and intuitive interfaces that work reliably in the demanding field conditions. Thank you.